Okay, so we look at two types of optimizations. One is the unconstrained optimization and the constrained optimization. Unconstrained optimization, there's only a cost, and you tune the variables so that you minimize the cost or maximize the cost. And unconstrained optimization is the one which is probably more useful, which will have constraints. So maybe you want to maximize the amount of money you bet on stocks, let's say, but you only have so much money to bet on. So that's a constraint. So let's talk about the simpler one first, which is unconstrained. Optimization. So here is a problem: minimize f of x equals 100 x2 minus x1 square plus 1 minus x1 square. Here we always write what we are going to minimize. So here we're going to, or sorry, the optimization variables. Okay, so if you're given this and you never really solve this problem before with fsolve, or sorry, with the tools which are going to use, the scipy.optimize, here are some ways you could proceed. You could graph this. Graph f of x versus x. Okay, now remember this is going to be a three-dimensional graph, three-dimensional plot. And I'm just going to make up something. This is f of x. This is x1. This is x2. And then when you look at the graph, since you're minimizing, this is the minimum. Right? So you can actually graph it and do this. But the problem with this approach is that you can only do it for 1 and 2 dimensions, right? If you go 3 dimensions, that is, there's x1, x2, and x3, it's just very hard to plot this on a 3-dimensional graph. So the second way is just guess, right? You can guess. Works sometimes, actually works pretty well. So in this case, it actually works. What you see in over here, actually I forgot to add a square here. There's a square here. What you see here in the cost function is this. This is a term which is squared, and there's a term which is squared. There are two terms which are squared. And you know, when there is a sum of squares, that term can never, that function f of x can never be less than 0 because it's sum of squares. So the minimum it can achieve is 0. So maybe we can guess that the solution to this will have, so say f of x is greater than 0 because it's sum of squares. So maybe the 0, which is equal to, is what is the solution. So we can set x2 minus x1 square equals 0, and 1 minus x1 equals 0. And so from there, you can see that from here, x1 equals 0, and then x2 equals x1 square equals 1. So it seems like x1, x2 equals 1. So this should be, my bad, 1. So this is the optimum. Okay, it was super easy because of what we guessed. But not everything is going to be sum of squares. It could be something more complex than that. Okay, so the third way is the way to go, which is something you might have learned before. If you have a function f of x and you're trying to estimate the minimum or maximum, what you do is you compute df dx, you set it to 0. This is known as the extremum. And then you check if d square f dx square is greater than 0, it's a minimum, or less than 0, it's a maximum. That comes from calculus. Now it turns out that you could actually check this df dx. So df dx, by the way, for a function here will be what? It will be, it's a Jacobian, right? F is what? If it's a scalar, x is 2 dimensions. So df dx is going to be one one row, two columns. We could actually do this. Oh, never mind. Let me just not do it. Anyway, when you do df dx equals 0, you actually end up with conditions which look very similar to this. You actually get the same equations. So there'll be two equations from the two columns. Each have to be set to 0. So when you set the first one to 0, you'll get this. When you set the second one to 0, you'll get that. And that's how you do it. Now, here's the interesting thing. Df dx equals 0. We have seen this. What's that? That's something we've seen before. It's basically root finding. When you root finding, you're finding f of x equals 0. Now we're doing df dx equals 0. So this is actually root finding. So you could use fsolve. You could take that first derivative of the function and use fsolve. It will work perfectly fine. In fact, what optimization will do is it'll take that, it'll find the derivative, and then actually use fsolve sometimes. It turns out that in this case, you can write an analytical expression for df dx, and then you can use fsolve. But for many times, you cannot write df dx symbolically. If you cannot do that, you have to use numerical methods to solve this. And that's where it gets kind of complicated. And that's why we'll not actually use our own techniques to, or we'll not write code to do that, but we'll just rely on what the optimized toolbox has to offer. Okay. So we will use scipy.minimize to do all these optimizations. Okay, so just get to the code, but this is the problem we'll be solving: unconstrained optimization. The problem is f of x. Let me see. Yeah, it's 100 x2 minus x1 square plus 1 minus x1 square. I believe it's the same problem. Yeah, it's the same one. Okay, so we'll just solve this. We know the solution for this one. x1, x2. We know that solution is 1 and 1, because if you put 1 and 1, you get f of x equals 0. And that's a minimum. Okay, so see how to do it using scipy. Okay, it's a very short code, it's just 12 lines. I put the documentation here. Essentially, we are trying to use scipy.optimize, and there's a function called minimize. I wrote it incorrectly. I should have written as scipy.optimize.minimize. I'll correct that. So once you import scipy.optimize, you just use the function minimize. Is basically the reason why there's a dot is because it's you basically create some kind of an object, and that object has a function associated with it, the function here being minimize, and you could have an object of an object. So scipy is the package, optimize is one of the suite of optimization packages. Within that, there are like multiple functions. One of them is minimize, and that's why we use minimize. So the question is, how do you know how to use this? Well, what I would suggest doing that is going to the documentation. So I just did scipy minimize. I went to the documentation. It tells you how to use minimize. You need to give the function. You need to give it x0. Any optimization method requires you to apply an initial guess. Without that, it doesn't work, because it starts with that guess and then tries to make an improvement over that. You need to give a method. Jack Hess. So the Jack is the Jacobian. So if you take the function and you take the derivative of the function, then you basically get the Jacobian. Now it turns out that the optimization will be much, much faster if you give the Jacobian analytically. If you don't give it, then it will estimate the derivative or the Jacobian numerically, which could be accurate, may not be accurate, and that will affect the speed of optimization. It makes sense to do this if there's a big, it's like if you have a giant expression and there are lots of variables, it makes sense to define this. But otherwise, it's good to be lazy and let the optimization figure that out. Hessian is basically the second derivative of f function. So it will be the derivative of the Jacobian. So the Jacobian here is a matrix. It's a matrix. So function is what? It's one scalar, right? X is the two variables, x1, x2. So df dx, so the Jacobian is going to be one row, two columns. But the Hessian is going to be the derivative of the Jacobian. It actually becomes a tensor. It's a three-dimensional matrix. It's much, much complicated. So people usually will just specify the Jacobian. They won't really bother with the Hessian because way complicated. Hesp, I'll skip that. Bounds would be if there are bounds. So let's say that we say x should be between, the x0 should be between -5 and 5. So that would be a bound. You specify that. Constraints, so this is unconstrained, so we don't bother with that. Tolerance, how to end the optimization, and so on. So these things what I explained are also over here. The method, there's like a variety of methods, and it actually gives you what those do. So for example, the one we'll use is a BFGS. It's called Boyd, Fletcher, G, I forget, and S is Shano. They're the four people who came up with the method. BFGS. So it's minimizes the scalar function of one or more variables using the BFGS algorithm. If you're curious, you could always search for BFGS. It's a very well-known method. Okay, Goldfarb is G. Okay, so it actually tells you how to do any optimization method usually needs a way to move forward. So let's say that you are at x0 and you need to climb. Let's say think of the function f of x like a hill or a valley. So if it's a minimized, it's a valley and you need to go down. How do you go down? Well, that basically uses the derivative. So it computes the derivative. BK, I think, is a matrix which comes from, okay, BK is basically it's essentially the Hessian. Hessian is basically the second derivative Jacobian. So it needs the Jacobian, it needs the Hessian, and then PK is basically how it will go down. So the Jacobian and the Hessian gives you a way to move forward. Now it says approximate Hessian. I said the Hessian is the derivative of the Jacobian. It's going to be a three-dimensional, it's a tensor, so it's a 3D matrix in this case. So 1 cross 2 was our Jacobian. Take the derivative of that with respect to x. So it's going to be 1 cross 2 for the first dimension, 1 cross 2. It's going to have 4 elements. So 2 elements for the Jacobian, 4 elements for the Hessian. It's usually n square. So think there are 1,000 variables. The Hessian is going to be 1,000 square. It's a big term. Anyway, so once you get that, it basically computes PK. PK is giving you the direction which to go. And then, there are like, it tells you that there's an approximation. So it's not really computing the Hessian. It basically is doing this. It's updating based only on the first derivative because the Hessian is time consuming to compute. It's n square, right? It's 1,000 square if it was n equals 1,000 variables. Anyway, so this is like a way in which you can update the sort of the search direction. How do you find the value? So these methods, which you will see, basically have different ways in which do that optimization. So Nelder-Mead is one more, which is interesting. It doesn't really use. So Nelder-Mead is a method which does not use the derivative at all. So what it does is basically, if there are 2 points, it starts with 2 points, and then it basically, so it starts with 3 points. So if you give it 1 point, it generates these 2 points, and then it reflects this point from over this line, and then it reflects this point, it'll reflect this point here, and then it'll reflect the other point, and then it finds the reflected point, which is the minimum value, and then it proceeds. It's a nice way to do this if you suspect that your function f of x is not smooth. Usually when you do an experiment on, let's say you're doing an experiment to figure out, people in rehabilitation do an experiment where we typically put an oxygen mask, where they're figuring out the oxygen taken in and carbon dioxide exhaled out as a metric of the energy expenditure. So that's something like that. A physical measurement is not smooth. It is noisy. Okay, so if the function f of x is noisy, here I give you a nice smooth function. What if it is noisy? Well, you cannot use the derivative. You're going to just take the derivative of noise. So what you do is you use something like Nelder-Mead, which basically does not use the derivative. So there are like methods which depend on the specific application you want. In this case, noise versus not noise. Sometimes it's the problem size which is important. The size, if the size is too big, then you want to use BFGS, which is basically going to give you the derivative without actually computing the Hessian. Okay, so let's run this, and we know that the solution to this is 1, 1, and it's still computing it. Yeah, there it is. So 0.99999999. That's because the tolerance was set to 1e negative 6, and so it gives you kind of there, but not really 1. So it's accurate to 6 decimal places. You could change the guess. I don't know. Let's try to do something which is very, very far away from the optimum. So 100 and 200. So I know for this one, it should probably work because the cost function is nice and smooth. So it gives 0.99 very quickly. It's just first time when you run it, just takes some time to initialize. Okay, so that's that. Now let's go to the next one. So most problems in the world are not as nice as just being unconstrained optimization. You normally have to deal with lots of constraints. So for example, if you're trying to start a business and you want to be profitable, you want to think of like if you want to, let's say, open a retail store, you have so much floor space and you want to stock it with boxes, and then those boxes take space. So you only have like, let's say, 5 products. You need to find what products you need to stock in your warehouse in order to make a profit. So then that becomes a constrained optimization problem. So most problems are like that. And for constrained optimization, you typically have a bunch of things which I will now specify, and then we'll solve a problem. Constrained optimization. Okay, so here is what I'll specify. Minimize f of x. Here x will be, let's see, x1 square plus x2 square plus x3 square plus x4 square plus x5 square. Okay, clearly x1, x2, x3, x4, x5 are our variables. And if there was no constraints on x's, you can see that sum of squares, the minimum has to be at 0, 0, 0, 0, right? That's clear. But if there are constraints, that need not be the case. So when you have constraints, you will put subject to x1 plus x2 plus x3 equals 5. Okay, so clearly if you put 0, 0, 0 is the answer, then it doesn't satisfy that constraint, because you look at 0 equals 5. So 0, 0, 0 is not the solution here. Another constraint is x. So you could have any number of constraints you like. x3 square plus x4 equals 5. x1 is greater than 3. Sorry, 0.3. x2 or x3 is less than equal to 5. x4 square plus x5 square less than equal to 5. So you see equals and greater than, less than, and so on. Okay, so here is what you should know. These are like things which will come up if you deal with optimization, and optimization happens all the time. Um, So this one is a linear equality constraint. Okay, it's linear because you do not have terms which are not linear. Linear terms would have be just x1, x2, the optimization variables. If you have x1, x2, that's non-linear because you have a product of two up to decision variables, like the x's. Okay, so this one is a non-linear equality constraint. Okay, so you have x3 square, that basically causes it to be non-linear. Here we have a non-linear it's going to be non-linear inequality constraint. Non-linear because you have x4, x5 square, and then inequality because there's a less than. Greater than 0 is also fine. Okay, so then there are two more lefts. x1 is greater than 0.3, x3 is less than 5. The way to think about those is you could think of those as linear inequality constraint. That's one way to think about them because x1, x3 are linear. And inequality because it's greater than or less than. But other way to think about this, and it will make your life easy, is because you could also introduce them as bounds. So when you're not given anything for x1 through x5, it means that they can range from minus infinity to plus infinity. But if you're told x1 is greater than 0.3, that means you're sort of going to bound it. So we can bound x1. So normally it is between minus infinity to infinity, but because the lower bound is 0.3, we'll put 0.3, and then x3, the bound is it's less than 5, so it could be minus infinity to 5. Now, x2, x4, x5 are unbounded, which means that they can take any value from minus infinity to infinity. So you're always better off trying to put them as bounds because it makes the life of the optimizer easy. It just has to put those in. When it varies the variables x's, it will never vary them outside those bounds, and it will make the life of the optimizer easy. So always specifies bounds as much as possible. Okay, so this is how you would, how this looks like. The same function minimize will solve this problem. Okay, we'll see how to do this using the same function, just that you need to specify more things here. So here is, and I'm going to give you two ways of doing it. There are more than two ways, but two ways. So here is, let's go back to this. Okay, so I have one method and another method. Okay, they just are using the same function. They're using opt minimize and opt minimize, same thing. But depending on what you use, the method you use, you need to specify it slightly differently. So here, this one uses SLSQP. It's also known as sequential quadratic programming, the SQP. You need to specify the cost. You need to specify x0, the initial variable. So I've specified 1, 1, 1, 2, 1. It needs you to specify equality, inequality constraints as one function argument. So in this case, I put all the equality constraints like this. You can see it's a type equality. So you're explicitly telling the optimizer these are the equality constraints. Okay, so there are two of them. And then this is the inequality constraint. So it doesn't care whether it is linear or nonlinear, but you just have to put them as inequality and equality. Okay. Then there is something called so options. It's just basically saying when you want it to converge, when you could decide it's going to converge. So 1e negative 9. Bounds is a function called limits. So if you go to limits, the bounds, I said the first variable has 3 to infinity. That's over here. Then I said the third variable has minus infinity to 5. That's over here. So lower bound, upper bound. And then remaining ones are minus infinity to plus infinity, minus infinity, plus infinity, minus plus infinity. Okay, so this is how you do it. And how I learned it, well, I usually try to find an example, copy paste it from their uh, take the example from scipy.optimize, put it in Python, get it to run, and then once it works, change the problem to correspond to what I wanted. I think this has examples, if I'm not mistaken. Yeah, so it has some examples. Okay, but with ChatGPT, you don't really need this. You could make it, if you just say you want to use SLSQP, it'll give you an example. Okay, so if you go up, it says there will be a method called SLSQP here. So it tells you how to call this function x0 method jack has Hessian and so on. We'll just go ahead and run this. So the solution it got, well, it gives some things. So the minimum value was 11.27. It took only 7 iterations. Function evaluations, how many times it evaluated the cost, how many gradient evaluations, how much time it did the df dx, so the Jacobian, and the optimum was 3, 0.675, 1.324, 0.245, and minus 1.69, almost close to zeros, 40 negative 8. Okay, so 0, 0, 0 is not the solution because of those constraints. Now, I did this another way. I used a method called trust constraint. Okay, so that one also has documentation. But here you specify constraints, nonlinear constraints, and bounds, just like the previous one. Here you specified like this op.linear constraint, op.nonlinear constraint, just a different way of specifying it. Here we had specified it this way. It was like a struct kind of struct. In a struct, you specify there is a name, a label, and then there's a definition for it. In this case, you just specify them in this fashion. Here it is. Okay, so that's the idiosyncrasies of the particular optimization. So the cost nonlinear function, you can see that instead of specifying it here, I actually went ahead and specified it here because it's more complicated. But then the other ones are simple. So I just specified in the same place. So let's run this same initialization. I can run it, and then it gives me actually the same solution. 3, if you remember, 0.675. This one was 0. We had seen that. It really doesn't matter. It's 1e negative 9. This one also tells you it took 68 iterations. Function 498. So you can see this one is taking a lot more time, a lot more function evaluations than that one. So this is important if you are solving a very big problem, or you're solving something which needs to be computed on the fly. Many of the things we do in robotics, you need the computations to happen at this very moment. You probably have like a few milliseconds to do this computation. So this was just a blink of an eye. We got the solution. Even 68 iterations didn't matter. But there are problems of bigger size where it should take 200 milliseconds. 200 milliseconds, whether it's very fast. That's like probably more than 100 milliseconds, the whole thing of me doing this. So you need it to be just like that, even faster than that, right? So here is 2 methods, and of course there are other ways you could do it. If you go to this documentation, you will see. In fact, some of them have constraints. You cannot use some of the methods. Let's just look at the one which you just used, trust constraint. This one, I think this is all fine. It has some other options you could put, but should be some notes on. So there are some best practices in optimization world. If you have a problem of a certain kind, what method should you use? This one, actually, if you go to MATLAB documentation, there's a similar function. It actually gives you the corresponding function in MATLAB is fmincon. I think this one gives you, I like the documentation. Unfortunately, Python is free. The perk of being free is that documentation is not that great. But this one is fairly detailed, and you could use the advice they give you here to apply for that. So for example, for the help choosing okay, so it actually tells you, this one has a fewer methods than Python, but it actually tells you what sort of reasoning you need to do. For example, you can always find an equivalent in the scipy package. So for example, it tells you interior point handles large sparse problems. So large means big size problems. Sparse is when you will see that the Jacobian is sort of will have many zeros in it. So the function f will be a function of few variables, not all of them. And so the derivative will be sparse. And then it tells you so it tells you what to use in case there's interior point. SQP satisfies, okay. It is not a large scale problem, so you don't use it for big dimensions. Legacy, active set, some with non-smooth, so it tells you what sort of, so this is like things which so finding the optimum is an art, okay, it's engineering field. There's no, it is not a science, unfortunately. So there's a lot of tweaking and tuning needs to be done. So you cannot just blindly fold one algorithm and say it'll work. It's going to be like a specific problem under specific conditions will have a different optimizer which will work. Then there are other tuning parameters constraints. So this by itself is like a field, people who develop algorithms, but even application of the algorithms itself a field. The other thing you will find is if you go and take a job as a data scientist somewhere, it's again going to be the same thing. Not all tools in data sciences can solve all problems, because if you could do that, then you could replace a human with a machine and it'll just do the problem. Many times you need the intervention. You need a human to go in and look at the data, make judgment call on which is the best method. You cannot optimize it. That's the good thing. It's like there are going to be jobs, even if we have ChatGPT, because of this element that you cannot fully surrender this to large language model. And when you see cool results, when people show amazing results, like on YouTube videos, they probably sit and tune these cost function and method, and then the variables within the top. That is not trivial. Okay, now if you have a lot of computation, you could just make like several thousand machines do several thousand combinations and come up with a setting which will work, but that's not scalable sometimes. Okay, so that's kind of the thing. This is not just some things which we've talked in the course were plug and play. They'll always work, but this is one of the things which is just an art. You have to play with different problems and different things in order to make something successful.